Hello and welcome to the lesson on calculating forces and lever arms based on our simple machines. So I want you to be able to explain concept of torque and be able to calculate it for a variety of real-world situations. So first of all, let's talk about calculating torque. So let's think about the wrench. So if I make a square nut, which seems to fit just fine here, torque is a vector. All right, so first of all, let's put it right here. Torque is a vector because it has both direction and magnitude. So it's going to be left or right and direction. So and into or, oops, I don't need the slash, I guess, into or out of page. All right. So really, you just got to give me a direction. You're going to tell me clockwise or counterclockwise. So how do you calculate torque? Well, the formula for torque is equal to your lever arm, so D multiplied by the applied force. Okay, so length of lever, and this one is force, perpendicular to lever. Has to be perpendicular to the lever for that formula to work. So here, we'll call that a fulcrum. From that fulcrum to where your hand is the length of your lever. And then how hard you're pulling at that point is your force. So there is your formula for calculating torque. And technically torque is a vector, so I better put a hat on. All right, so let's do a couple of examples with torque. So we have a 30 centimeter long wrench, so I'm going to keep my wrench simple. There's my wrench, 30 centimeters, but I need it in meters. Still have to work in meters and newtons. It's rotated counterclockwise. So if here's my nut, rotated counterclockwise by a 100 Newton force. There's my 100 newtons. Determine the torque. So torque equals D times F. So 0.3 times 100 equals 30. Now, what is the units here? Well, it's our D is being calculated in meters. It's being multiplied by newtons. So the units for torque is Newton dot meters. All right. Now we need a direction. So is it into the page or out of the page? So everyone's heard of the lefty-loosey, righty-tighty rule. Lefty-loosey, righty-tighty. Okay. So if it's left, basically you are rotating it left, you're loosening it, or the screw is coming out of the board for you. So that is out of page. And if it is righty-tighty, that means the screw is going into the board. So that means the direction would be into the page. So because we're going counterclockwise in this situation, all right, so lefty-loosey, righty-tighty, remember that. Father yelled at me about that over and over. I still get it messed up. Probably because I'm in a hurry and I never want to think about it. So lefty-loosey, this time it is rotating left, okay? We consider that left over here. So that means that it is going out of page. And you just got to write out for me. So therefore, 30 Newton meters out. Okay? So there we've calculated the torque of a wrench when you're working and tightening a nut, or loosening in this case. So calculating force acting on levers. Well, I'm going to jump down here for a second. Again, here's our fulcrum, right here. So remember, first class lever. The first class lever is when the fulcrum's in the middle. So we'll have a load force and we'll have an effort force, which should be going the same way. And this distance here from force to fulcrum is your effort load, or sorry, your the length of it. I've got a bit of a brain cramp, but your load arm, sorry, load arm. And this one, load arm, is right here, so DE. So going up, the formula for calculating this is simply your effort force, so FE multiplied by DE. It will equal FL multiplied by DL, which makes sense. If you're going to move something, the force, or the one side of the equation, should equal the other. So if I know that my load is 100 newtons, or whatever we're calculating, then I know that this has to give me a value of 100 in order for it to move. Second class lever is fulcrum at the end, the wheelbarrow. So here's my load, here is my effort. I'll just change color. So this is my DE, and this is my DL. Third class, I have my effort in the middle. Here's my load. So as long as you can figure out where the measurements come from, then this is not a difficult task. You should be all right. DL. All right. So there is the formula, and there's your three classes of levers and where all the information lies. Okay, it's all based on the fulcrum, where your effort force is and where your load force is. So an example, I've got two examples, don't have any information yet, so let's put, let's go 30 newtons over here, and that's going to be my load. This distance here is 0.2. This distance here, I'm going to say is 0.3. So what is my effort force? Okay, so we're looking for that unknown. Well, we know the formula is load times DL has to equal effort multiplied by DE. Okay, so FL is my load force, which equals, it was 30 newtons. DL is the distance from my effort load to the fulcrum. It would be 0.2. Looking for effort force, so it's the unknown, and it's 0.3. For the distance between effort and the fulcrum. Formulas are always the same. They're nice to solve. You got to divide both sides by 0.3, and we get 20 newtons. So therefore, FE is 20 newtons. So I only had to apply a 20 newton force to lift something that was 30 newtons. Next one, I'm going to put my effort force at 100 newtons. I'm going to put my load force, so wheelbarrow, at, let's go with, let's say 400 newtons. The distance from my load force to the fulcrum, I'm going to say is 0.4 meters. How long is the handle on my wheelbarrow? Okay, it is the same formula. So FL DL equals FE DE. Plugging in our information. My load 400. I know it's 0.4. I know my effort force. I'm only putting 100 into it. So how long is the handle on my, oops, how long is the handle on my wheelbarrow? So I get DE will equal 4 times 0.4 be 1.6 meters. So therefore DE is 1.6 meters. So the handle of my wheelbarrow is 1.6 meters, which is fairly reasonable. 2 meters is about 6 feet. It's about 1.5, so you're looking at about a 4-foot length. And if you go look at a wheelbarrow, your average wheelbarrow is about that length. So again, I want to emphasize, if you look at the comparison here, when you're only lifting with 100 newtons of force, I'm lifting 4 times that amount in terms of load, okay? And the distance, like I said, is only about a 4-foot handle. So the wheelbarrow gives you an incredible mechanical advantage. That's why it's still widely used in construction sites. One last example. This is the one, you'll have more space than I will. Let's bring that down. So there's my fulcrum. So this is the fishing pole example. So let's say with the fishing pole, I'm going to twist up at, let's say 8 newtons. And fish, let's say I've caught, 10 kilogram fish, so that's about 98 newtons. So this is my load. This is my effort. All right. My hands fairly close together. Let's go with a length of, say, 10 centimeters, so 0.1 meters. What is the length of the fishing pole to make this work? So effort force times dE is equal to load force times length of the fishing pole. So 8 newtons, dE is 0.1. We know the load, 98 newtons. So what is the DL here? The down low. I'm kidding. I'm not trying to be that hip. All right. We calculate it. And when I do this calculation, it comes out really funny. And this is what happens when I make the example up in my head. It tells me that it's 0.008 meters, which doesn't make a whole lot of sense, does it? So if you multiply by 100, it's 8 centimeters in length. So if I want to haul this fish in, okay, 8 newtons is not good enough. All right. So that means that my load force, or my effort force, is going to have to be much greater than my load force. So the average fishing pole, let's just talk about that for a second. A fishing pole is about, let's say 6 feet, so that would be about 2 meters. Okay, so let's try this situation again using the 2 meters. So now I'm going to use, fulcrum still here, effort force. I want to know what my effort force would have to be to haul this fish in. All right, so there's my 2 meters, and we're talking about a 98 Newton fish. That's only 10 kilograms. So FE DE equals FL DL. It's kind of interesting when you get a really funny answer that makes no sense. Talk about the Y here. So effort force is what I'm looking for. My DE is 0.1. FL, again, a 98 Newton fish, 2 meters. So we divide that by 0.1. And what does that turn out to be? So 98 times 2 divided by 0.1 is an effort force of 1960 newtons, which is incredible. So if you want to haul in this fish, you better space your hands out a lot wider, because 1960 newtons is quite a bit of force in order to do that. It's a lot of effort. So the fishing pole is not exactly your most efficient lever. I wouldn't recommend it for doing a whole lot of heavy construction and lifting. But maybe that's why fishing is considered a sport, because it's a little bit of a workout. Okay? I'm just joking. If you're a fisherman, don't be angry. All right, so there are your 3 examples of calculations with levers and torque. Like I said, the nice thing is that's the formula that we are that you're going to need for all levers. It doesn't change. The difficult part is for you to identify the different variables and the values from the given diagram. If you have any questions, make sure you ask, and I'll clarify, or we can talk about a what-if situation in class. So we'll see you in class.